Good day everyone! Today, we will gonna talk about polyprotic acids. Definition of polyprotic acid. It is an acid that can donate more than one proton in an aqueous solution through multiple ionization steps, meaning it can donate or give away more than one proton when it dissolves in water. Each time it donates a proton, it goes through a separate steps, and this step is called ionization steps. Each step has its own equilibrium constant or Ka, which shows how easily an acids give up that protons. Categories. Remember, polyprotic acids are classified based on the number of protons they can donate. Diprotic acids, which means it can donate 2 protons. Triprotic acids, it can donate 3 or more protons. Equilibrium stages. Each proton is lost in a separate equilibrium stages or steps with its own dissociation constant or Ka, meaning that each proton is released one at a time. The first hydrogen ion H+ is released easily. The second one is released less easily. If there's a third, it's released even less easily. Each release step has its own Ka value showing its strength in that stage. Polyprotic acid. Acids that can donate more than one proton per molecule in an aqueous solution undergoing multiple ionization steps. This means that when these acids ionize or release hydrogen ions, they do it in multiple steps. Each step removes one hydrogen ion at a time. Just think of it like a peeling of an ion. Each layer represents one hydrogen ion being released. Let's proceed to their categories. So in diprotic acid, this means that acids can donate 2 protons or H+ per molecule. The first hydrogen ion is released. Then the second hydrogen ion H+ is released. Example, sulfuric acid H2SO4, carbonic acid H2CO3, oxalic acid H2S2O4. Let's proceed to triprotic acids. A triprotic acid is an acid that can donate 3 protons per molecule in an aqueous solution through 3 ionization steps, meaning it can donate 3 protons per molecule. Ionizations happen in 3 steps. So the first step is ion H+ is released easily. The second one takes a bit more energy. This one is released last and it is the hardest to remove. These are its examples: phosphoric acids H3PO4, arsenic acid H3ASO4, citric acid C6H8O7. In short, diprotic acids releases 2 ions in 2 steps. Triprotic acids release 3 ions in 3 steps. Key characteristics. Each ionization steps affect pH and buffering. Polyprotic acids ionize in steps, and each step affects the pH and buffering ability of a solution. Important in buffer systems. They are important in buffer systems like the phosphates buffer that helps maintain a stable pH. Some intermediates are amphiprotic. Some partially ionized forms are amphiprotic, meaning they can donate and accept protons. Conclusion. Polyprotic acids donate multiple protons in steps. Each step has unique equilibrium behavior, and it is crucial in chemical, biological, and environmental systems.
For our example, we got sulfuric acid, H2SO4. And in this case, we got 2 hydrogen or 2 protons to give. First breakdown, H2SO4 will be breakdown into H+ plus HSO4 minus. Now, for our product, we get another H. So let's break it another. In this second breakdown, it will be equilibrium. So, in any case, bali-balihon ang equation, same lang gihapon. For HSO4 minus, breakdown to kuan og H, mag-donate og H plus SO4 2 minus. In that case, we don't have any hydrogen to give more. For the next, the multiple dissociation and Ka. For the first breakdown or dissociation, it can be Ka1. So, the more we break down or the more we dissociate it, the Ka will be lesser, and they say that larger Ka will be more strong acid. So, the more dissociate, the more less Ka, the more it will be more less strong acid. Then for this case, the ICE chart or the ICE chart, there are two breakdowns or natay duha pod ka ICE table. For the first ICE table, ibutan na to ang acid. H2SO4 break to H plus HSO4 minus. For the I or the initial or what we call the moles of it, first we will use a variable. We will use the hashtag or the number sign. Then the product will be 0 and 0. For the C or the charge, for the reactant, it will be negative X. Then for the product, they're both positive X. And then, we will combine it in the E. Number sign minus X equals number sign minus X. 0 plus X equals X. 0 plus X equals X. Now, for our last product or the HSO4 minus, the end product of it is X. Now that we will bring it to the next table for the SHO4 minus. For its initial, we will use the X. For the product or the 2 will be still 0. For the C, we will use another variable since nagamit ang tag X for the first table, we will use Y for the second table. Still X, still negative Y, plus Y plus Y. We will combine X minus Y in the end, X minus Y. 0 plus Y equals Y. 0 plus Y equals Y. And for the Ka1, it just be for the end table, we will look the Y from the products. Y times Y will be Y squared over X minus Y. And that is how the ICE table works.